Hey, Lakshmanan. Hey, Rahul. Nice to see you. Yeah, how are you feeling? Pretty excited.
Yeah,
Yeah, good day.
yeah,
Go on.
good day. Beautiful location. We're right at the edge of the Atlantic Ocean. Rockets at the back. Things are looking pretty good.
Yeah, very good. Very good. We're just running through final checklist.
Yeah, that's awesome. Well, that's actually what we have here. In this conversation, it's pretty heavy, 70 pages of checklists that you guys go through every single time. So obviously we're not going to go through every single detail, but I wanted to maybe give our viewers some idea of just the immense level of detail that we go through. But before we do that, um, can you just maybe briefly introduce yourself? Tell us your name, of course, but you know, a little bit of your history. Why do you care about rockets, education, some of that kind of stuff? That'd be really cool.
Yeah, for sure. I'm Lakshmanan. So I started working with NordSpace 3 years ago. So I was the first employee. So I'm so happy to be part of this. So now my role is chief propulsion engineer. So majorly work on engines, cooling channels, and heat fluxes, anything that combusts. I'm directly responsible for it. I also work with other mechanical engineers on the team. I help them design mechanical structures and analysis of mechanical structures. So that's my role here in NordSpace. My background, I started as a mechanical engineer. So I used to work with IC engines, where car internal combustion engines. That's my background. I've been always interested in aerospace and space. As a kid, I always wanted to go to space, and I still do. Hopefully one day.
Yeah, we'll make fun of it.
Yeah. So as I moved through mechanical engineering, I always liked something that's burning or propelling towards very fast. So that kind of directed towards the engine criteria. And then I took my master's in University of Toronto, and that's where I took combustion and aerospace propulsion, then not space.
That's awesome. It must be pretty magical for you because I remember NordSpace started, we didn't have an office. I interviewed you in a basement cafeteria somewhere. Um, and we started blowing stuff up on my porch. I still remember that. Then we moved into for us, giant facility, and it was just the two of us. We're just wondering what the heck we got ourselves into.
It's a massive facility, it looked like.
And there was nothing in there. Yeah, nothing, just dust. And it was just the two of us. We had a huge boardroom, and just to make it look like it was full, we got a giant boardroom table, all just for the two of us.
Yeah.
Crazy times. And that was like barely 3 years ago. Now we're headed towards 25 people on our team, some of the most talented engineers and scientists. We have a rocket ready to launch. We built our own launch site. We've acquired all kinds of manufacturing capabilities.
Yeah.
How does it feel?
It's crazy upgrade. Honestly, I never thought how big this is going to be. I know it is going to get bigger, but as you see it progress, that's a beautiful experience. And especially with the launch site, we have a big road, we have a pad, and we have a rocket now. And then we have more people on the team who are experts in their own fields. It's really crazy and very, very exciting.
I think one of the biggest challenges you have is not just designing the rockets, but you know, one of the things that's very hard to appreciate, especially when you're designing high performance rockets, like if you're just, if we're just talking about like toys where you're solid rockets or you light it, it goes, but our margins are so small for everything, and not just the technical margins. You know, we as a commercial company, a lot of us did rockets as students and stuff like that. But we have budgets, we have payrolls, we have timelines, we have and I know you must feel me breathing down your neck sometimes, and I really try not to. But still, there's so many other pressures, right? When you're doing this professionally, how s- so how slim are some of the I've seen you on the absolute edge, and I think one of the things I really admire about you is the confidence you bring to the team when you're able to make that really hard decision, whether to run an engine or not, whether to launch or not. Um, can you just give people a sense of how slim are the margins when it comes to rockets, mass fractions, things like that?
So yeah, that's a very deep question to answer. For example, I can take Taiga as an example. So the mere change of about 5% on the pressure would just spoil the entire mission. both on fuel or liquid oxygen pressure. So just 5% on the pressure difference would cause a lot of combustion instabilities and cooling problems and everything. The same goes with every single thing across the systems. We have multiple actuation techniques for valves. We have cooling across the channels. We have injection velocities. So all of these things have their own margins. But the thing that is not completely intuitive is that these margins add up. So let's say specifically for the fuel pressure, it might seem 5%, but in real life, it's not 5% because it is being added up on other tolerances like injection velocities and injection pressure difference. And at the end of the day, you're just looking at I can throw in some numbers, but we're looking at 0.05 megapascal pressure difference, and that will screw our mission over. So that's our margins with just pressure and technical things.
That's wild. Yeah, I mean, like, suppose we were to how take Taiga for example. How thin are the walls of our tank? Order of magnitude. I know we don't want to get into too many specifics, but
Um, I can give an interesting comparison. So if we hit the tanks hard enough, we might be able to bend it. And these are Inconel tanks that we're talking about, which are superalloys. They're called superalloys for a reason. They are 2 times the strength of steel on a normal Inconel 718, whereas they're 3 times as stronger if they're heat treated. And so, but I don't want to get into the exact.
well, what I was getting at is what happens if you were to increase the thickness by like 5%, right? Mass increases, so it's like, okay, if you need the same form factor, then you need more. You need a beefier engine, and if you need that, then you need more pressure. You need more fuel. That increases the chain reaction of the smallest thing.
Exactly. So even not increasing, even just replacing few items in different spots will completely differ the mission. There are a few components which might be heavier, and we want to place it in the right orientation as well as right position, which changes the mission criteria.
The precision is unbelievable, and I think that's one of the reasons this mission is so important because it's we're doing everything we can to almost. It's a really critical step for orbital because it allows us to go into uh, in some cases even greater detail than we may in orbital because our margins are slimmer, with a suborbital flight. Um, but we're trying to scale everything up to orbital. So including our procedures. I think one of the most important things that we've learned and we're learning is how do you manage an operation for a professionally built liquid rocket system. And so what I'm holding right now is basically a binder of 70 pages. Our team goes through this every single time we set up. So they were here this morning. We were here at 3 a.m. and we go through hours of detailed checklists. Again, this isn't just about like inserting a rocket motor into a shell and lighting it. There's a lot that goes into this. So of course we can't go through all of that. Not only do we not have the time, but a lot of it I know is very proprietary. But maybe I'll just flip through some parts of this, and I'd love for you to give me some insight into things that you think are important. Um, so in 70 pages, it's a lot. Even things down to like our communication protocols. So tell us a little bit about that. Like when we started, I remember when we started, we were just kind of like back in the day when 2 years ago, we were just kind of like yelling at each other.
Yes.
And now it's like a very precise way of communication. Why is precise communication so important to a launch campaign like this?
Any misinformation or any changes in the system should be known across the board. So in this case, any miscommunication in terms of wiring or in terms of valves, that causes a large issue. When it is not traceable, that becomes a bigger problem. So every single communication goes through the protocol, and it is being recorded in such a way that we can trace it back in case there's any issue.
Right. Yeah. Super important. So let's talk a little bit about range procedures. So we cover things in this checklist like range layout, distances, safety, site safety, ballistic, hazards, weather monitoring, and you get into a lot of detail into all of this. But tell us a little bit about range procedures and why this is important.
So on the pad, we're storing propellants, and we want to make sure everyone is safe. Everything is operated safely. For example, there's different procedures that we have to go through. On a higher level, we bring the rocket down, we fill up fuel, make sure that the pad and the range is safe, just in case if there's any public in our range within the explosive diameter or within our dispersion rate. We have to stop the launch. We have to figure out what the problem is. So that's our general way of operation. And then once the pad is yellow, when the pad is yellow, what we mean is that the propellants are getting filled up. So during that time, we don't want anyone near the pad except for the launch technicians. So they do all the setup, and once they're out, the pad becomes red. So pad becomes red, meaning no one goes near to the rocket because the rocket has igniters on, the rocket has oxidizer, as well as fuel on. So it is a potentially launchable rocket at that point. So we don't want anyone in the pad. So we do the drone scouts, we do road control. As the mission control officer, we should make sure that anyone who's on the pad, who's out of the pad, and anyone who is on the less than 300 meters into the site. So we keep track of everything. We keep track of the members of our team, as well as members who are from outside our team. For example, the fire department, Transport Canada. So people, external stakeholders, we also maintain the list of people who are within our perimeter, just to make sure that everything is operated safely, and that is also traceable across.
Awesome. I see a couple different roles here. So we have launch director, we have range safety officer, mission control officer, chief technician, launch technician 1, 2, 3, avionics 1, 2, software, all kinds of roles. And you are which one, Lakshmanan?
I'm mission control officer.
Awesome. So you're one of the two people, Hubert, who we also have a great chat with, in mission control.
That's correct.
How does it feel being in mission control?
It is. I mean, it is exciting as well as stressful at the same time.
Right.
So I'd be lying if it's not stressful. So we are controlling all the valves. We're monitoring the pressures, temperatures. So we have to be very keen, very silent. Yeah.
Yeah. Yeah. That's awesome. To skip through a couple of things, but I just want to. There's a lot of precise numbers in everything. Like for example, safety clear zones being like X number of meters, down to the meter. So I know you've all done a huge amount of math, calculations, simulations using industry standard tools, professional tools for orbital rockets and all of that. How important has it been to learn every little detail that'll scale up to an orbital mission, around, site safety, safe distances, explosive radiuses, radii, things like that?
That has been the major learning from this launch campaign for us, because we have tested everything in our test site, and we have mostly our internal people. We maintain the safety regulations which are required for that site. At this point, we're dealing with dispersion rates, explosion rates, and we're storing propellants here on the pad and the launch pad's radius. So everything matters here. And the good thing is we have regulations for every single thing, which is based out of FAA's regulations. So we keep track of every single kilogram of fuel that we have on the pad. That will translate into down to the meter for the explosive distance. So that's the major learning. And also by doing the research on that, we can see how this whole explosive radius, everything scales up for our orbital. Since we have our orbital sizing, we know exactly how much fuel or how much propellants that we'll be storing in an orbital launch site. So while we do this calculation, we also make sure that, our current site, is it capable of handling an orbital rocket? Is it capable of handling the bigger orbital rocket? So that's been our major pushing on this launch campaign. And we're glad actually that we got to do those calculations, because these are more regulatory calculations, which as a technical person you wouldn't be much involved in it.
Yeah.
So these are new things.
I think that's probably one of the biggest things. Our team is almost entirely engineers. Like I said, we've built rockets, obviously nothing like this one technically, but also we've never had to worry about, making sure that people who want to go fishing are safe and people that want to fly over, crossing from Europe, the Atlantic to come to Canada are safe. Um, to make sure that our own staff are safe. I noticed you have cryogenic safety gear here, and all kinds of other things, fuel storage and all this. So there's just so much to consider, and I'm really happy to see all of this because obviously all scales up to us for us as we go to orbital. Let's talk a little bit about the rocket integration checklist. So section 10 here, um, very interesting flow diagram. Um, just how important is this in order for us to be ready to launch the rocket integration checklist?
So the rocket integration checklist has major components, including the mechanical structures as well as the flow control devices. So every time that we move the rocket, there is a chance that some of these fasteners might come loose. So we want to check every single fasteners across the rocket, just to throw rough numbers. Just on the engine bay, we have more than 100 fasteners. So that's the checklist. That's why it gets more details in them, and we check every single bolt and nut across the rocket.
Yeah. Yeah, I see, like, dude,
Yeah.
intertank each intertank has its own integration checklist. Each, the engine bay has its own, avionics bay, brief flight integration, launch rail assembly, and these are, like, each of them has, like, dozens of items.
So in this, as we know, this is about 70-page document, but there are a few systems which actually track into another document which has like another oh my god pages. So
Yeah, yeah, that's not easy, but, checklists are just so valuable, and it's an iterative process as well. I see that you just this document alone has I can't even count how many revisions because you go through the process, and every time you go through, it, you learn something new. You see that you might have forgotten something, and you insert it into the checklist. Every single detail matters.
exactly. So there are a few things that we'd like to improve to speed up the process. So that's a revision. On the other hand, there are a few things that we would have genuinely missed. So those are additions and new revisions that come on.
Awesome. Wow. Yeah. So I'm scrolling on my phone just to make it a little bit easier, but I'm still scrolling and going through the checklist. Launch procedure. This sounds exciting. So, tell us a little bit about this. We have a checklist related to launch readiness, GC integration, and health checks, rocket health checks, fuel fill, launch rail integration, launch rail raising, pressure and fill up, oxidizer fill up, all the ignite, so many things. So, um, what's this whole section about?
the That's a step-by-step procedure. Once everyone's on the pad, we need most of us here on the pad to get the rocket ready. So the health checks are required for all the flow control devices, all the mechanical structures, as well as electronics, avionics, and any GPS devices that we have on the rocket. So everything goes through each of these checklists. The checklists which we saw previously, they are before the rocket's on the pad. Now, the launch procedure mandates everything to be checked once again on the pad before we slide into the rail. So that includes all the pre-check processes and re-health check, and then we move on to lifting the rail. Rail also is a completely separate beast because it has to
So
hold
it's its own engineering system. It's its own thing.
exactly. So we have a separate checklist for all the fastness on the rail, make sure all the actuation systems are working on the rail. And once the rocket is lifted, most of us will be going back to the mission control, except for the launch technicians and LD, launch director, and RSO. So these guys will be here to make sure all the propellants can be loaded. They're doing all the preparations there. So launch procedure includes the safety systems that are in place, and that will tell them where it is. So it will point them in the right direction. And also it reduces the amount of thinking that you have to do on a pad itself. Um, you just go through the checklist step by step, and each of the step are sequential. So that's the pad criteria. Then once the pad is clear, once the pad is red, uh, every single thing that you mentioned just now, like locks filling, pressure filling, everything will be done from the mission control. So the whole point of this procedure being that strict is that once we're all in the mission control, no one is on the pad, and we have to be sure that we get the maximum control on the rocket, both for launch as well as for safing the system.
Awesome. Well, saving the system, that's an important thing. So we obviously had one single basically attempt in August to launch. Unfortunately, the hurricane and just, like literally teething issues. Like we're learning along we go as we go along the way, including all the people around us, stakeholders from the local community to the regulators and all of that. This is new in a lot of ways for Canada. Commercially, I mean, it's a whole different beast. And then on the safing side of things, we had our safety system kick in. We're obviously like, we could have got that launch, but it's okay. Any launch attempt where the rocket's safe, people are safe, that's success in our minds. I'm gonna skip through a lot of things. I know you have to get back to the pad. Mishap procedures. Obviously, you never want mishaps to happen, but this is something that you really plan for. I can see a ton of detail here as well. And this is literally rocket science. Things can happen, and so we want to be prepared for it. How important is it for everyone to understand these mishap procedures?
So we've gone through different ways of mishaps that might happen for a rocket, as well as launch pad, as well as for the public. So we keep intense amount of details and strict rules for amount of storage, fuel storage, or how we operate. Even tiniest thing like the fabric that we use on a launch day, it has to be non-inflammable, cotton based. So things like that, we keep strict regulations on those. And any mishap, we also have.
I know I've heard, if sorry to interrupt, you don't even want people to wear electronic watches the record oxygen because you're worried that it can spark.
If it is not intrinsically safe, we don't use them near both our fuel as well as liquid oxygen.
Right.
So we have safety distances. So one we have a buddy system mostly when we work. The other person will be in a safe distance, making sure all the works are done safely. So these are all pad works. And then once we're in the mission control, most of the things are automated. So we have safety sequences and shut off sequences, which will safely relieve the pressures on the rocket. We also have methods to save the rocket when we lose complete control on the mission control too. So there are a few analog mechanical systems that will make sure that the rocket's not fully pressurized. It evaporates all the liquid oxygen and keeps the rocket completely safe. So in spite of all these things, we also have muster points. We also have pathways where people have to exit through in case of an emergency. We have multiple fire extinguishers across the site.
And then we have the fire department.
We got the fire department too. Yeah.
There's a lot that goes into this. For sure. And this isn't just something that you guys review at the pad. I've seen you late nights kind of going through readings with everybody around the room, and like just talking through it. Kind of like actors, they go through a script. Before and so there's just so much preparation. But this is what's required. I mean, if we're serious about doing this as a company, as a country, and we are. We have to do it right. We have to make the right design decisions. That's why we chose the propellants that we did. That's why we chose, liquid propulsion. That's why we chose the architecture, the payload masses and everything to be competitive to, you look at the US, you look at countries that are really like, they've been doing this for a long time. We're following in their footsteps. We're choosing to be innovative in the right places, and choosing to follow standard procedures. Where it's already been done. So I'm really proud of you, Lakshmanan. I'm really proud of the team. Anything you want to say finally before I let you go?
Oh, thanks for this opportunity. It's really been exciting, both for this interview as well as for whole NordSpace. I've got great experience so far, and we're all excited to go for orbital immediately after this launch.
I know you've been itching to work on those turbo pumps and and the larger engines and all of that. We're just days away now. Congratulations, Lakshmanan, for everything.
Thanks, Rahul. Yeah.